Okay. Don't know that I'm getting the screen. It's clearly very light. Did you get it this time? It's awful blurry. But camera, since the camera does a lot of neat things. I thought maybe you need to show the orange one. See? Look. Okay, now you got it. Okay. Oh, your camera. Okay, so you want to parameterize circle radius capital A in the YZ plane. That was the original question. Well, there's a circle here. We'll get around to parameterizing this in a minute. Turns out we needed to kind of review how do you do parameterize circle radius, whatever. Well, again, two cosine u I plus two sine u times j. Okay, now the reason I use t, I use t. And that's compounded with what we've done here. So after graphing and figuring out a few vectors here and approximating them, came up with a picture that looks something like this. Okay, that's reasonable. And of course, I'm not going to explain why R of pi over 4 is approximately 1.4 I plus 1.4 j. You just plug pi over 4 in. See, but better, you look at your unit circle, see that pi over 4 is here. That's going to be about 0.7. That's going to be about 0.7. And I mean, wrote it out. And it said R of t, that's R of pi over 4. Is 2 times cosine, just 2 sine, cosine squared of 2 over 2, 2 sine squared of 2 over 2. And the cosine and the sine are approximately 0.707 at that point. So rounding that off to 1.4, we got this. Then we got these numbers, and now here's our R of t. Here's the shape, approximate shape, traced out by the tip of the R of t vector. Okay. So what shape is that? Well, that's what's the magnitude of R of t. Okay. And got it. Straightforward, right? So you just take square of this plus the square of this. Now that's for this R of t function. Okay. But then we generalized. I said, okay, now let's just get rid of this, and we understand all this. I posed the question how you do the interior. So, okay. Well, that's going to consist of circles that have every radius from 0 out to 2, right? Circle of radius 2. And we see that if you got a 2 in front of the cosine and sine, you get a circle of radius 2. Well, if we got a parameter v out in front, then you get a circle of radius v, right? So if you want a circle of every radius from here to here, just let v go from 0 to 2. There we have it. Okay? Make sense? Okay. Well, that's how you parameterize a circle or the interior. So now we'll come back to this one in a minute. But in your parameter space, now you've got v, you've got u. U goes from 0 to 2, 5. V goes from 0 to 2. So here's the parameter space. If you partition the U interval and partition the V interval, partition the U interval, you get all these vertical strips. Right? If you partition the V interval, you get all these horizontal strips. Okay. Now your function maps this rectangle to this circle. There's your circle. The horizontal lines over B equals constant. When B is constant, what shape do you get down here? Just show me with your hands. What shape do you get if you hold B constant? You get a circle of radius V. Okay, so every one of these becomes a circle of radius V. I'll get rid of the story. You get the idea. Okay. And what happens? Well, what do you get for constant U? Well, U is the angle you're taking the sine and the cosine of, right? For example, if U is pi over 4, then you're going to get points on the right as out from the origin of an angle pi over 4. Okay. If you're holding the angle constant, you're plotting x equals cosine, y equals sine. Okay. So no matter what B is, this vector always has the same direction if you fix U. So these vertical lines I'm drawing some of them, but this is a schematic. Give you these, right? And your typical region typical regions like this, right? Dimensions. And you got a little arc here. On these sides, it's nearly a rectangle, but it's narrower down here than it is up here because, of course, these lines spread out. Well, this should be familiar to you, but this is delta V. And this is a V delta U. This is an arc of a circle, a radius approximately V. Okay, now if you go to sample points, okay, you got a sample point in some rectangle here that maps to this rectangle. So there's the sample point. So it's V star delta U sub I, if you wish, you go to V sub I here. Okay, which is just like you got the point R star, theta star is polar coordinates. This is your R star, and put substance on substance, and then R I star delta theta I by delta V I by delta R. R V. Okay. And that should be familiar to you because that's how you do polar coordinates. That's how you bring polar coordinates. It's your area increment in polar coordinates. Note that these are perpendicular, obviously, and these are perpendicular because the radial line is perpendicular to the circle. Okay? They're nearly perpendicular because, of course, these are arcs. If you shrink it down, these become straight lines. These are curves. Okay. Okay. Well, that's an important image you got to carry along. But let's now just stick with this. And let's tackle the question of and what shape do we get in this parameterization? Okay, good. We can very quickly recognize that this is a circle of radius v, and this is v squared. And if you graph v squared versus v, you get a parabola, right? So we'll call this, let's see, because that's originally equal to v squared. This is v, it's a parabola. And of course, v is, it's the same parameterization we used before. Let's go ahead and write it out. 0 less than or equal to u less than 2 pi. 0 less than or equal to v less than or equal to 1. I would have been 2. Okay. So v goes from 0 to 2. It looks like this, right? Okay, well, take this over to now you've got a circle, radius 2 down here. And for every circle, okay, for this circle, you're going to go up 4 units, right? If you're on the outer circle, v is 2. The position of v equals 2 circle. So v squared is going to be 4, right? So you have your vector here, which would be your v cosine ui plus v sine u. Okay. And then you can have your vector here, which is, and it's actually 2 in this case, 2 cosine ui to the outer part of the circle. Now you're going to go up 4 units. Because now this is 4K. Right? That makes sense. So you got your v cosine ui plus, okay, for v equals 2, you got your 2 cosine ui plus 2 cosine uj plus your 4K. What's that mean? Your r vector is out here. I don't want to draw it, it's going to get in the way. So you've got to see your r vector. Okay. So what you're going to do, you're going to say that, okay, let's see if I can make this work. Okay, so above this circle, you've got a circle 4 units higher of the same radius. Well, if you want to go to the circle of radius 1, you're going to have a circle 1 unit higher. But circle radius 1, that's your v equals 1 circle. So you come on up 1 unit. Now that's 4 units. 1 unit is not that far. And we'll come up about this far. And now you have a circle out here. You've got this circle and you've got this circle. Down here, you just have the point of the origin. Well, what you got? Something like this. The circles keep expanding as you go up. As V increases, the circle that you're going to lie above gets bigger. And the z coordinate gets bigger by the square. So it's a parabola. Now, you really need to be pretty familiar with quadratic surfaces, not to mention parameterization of curves. Okay. That's from the first chapter we looked at. Okay. But there you have a parameterization of parabola. Make sense? Okay. So you get a lot of mileage out of being able to parameterize a circle. Okay. Because B is just going to be the radius of the circle down here. And well, let me respectfully erase this. You just have your parabola going. Well, actually, that's right. If you turn it upside down, you pretty much get something that looks like this. So had it on the side. So I wasn't quite sure what you were doing, but I was sure that you were seeing something. It turned out you were pretty much seeing it. But you want to carry that through all the way to the little details. Let's go back. Quick exercise to this circle. Okay. I'm going to parameterize this circle. The circle of radius A. Okay. And it's apparently on the y-axis and the y-z plane, right? So see if you can come up with a parameterization for that circle. Okay, so after having seen this, and we'll come back to it, but we did one thing I wanted to do before we went on, which is parameterize this circle. People have trouble with this, okay? Not enough work on transformations and pre-calculus. And of course, you know, if that's really internalized, then it becomes kind of obvious because this has very similar characteristics. Okay, so you know what everybody came up with was just this. Okay, but that's just this circle. Okay, the circle we saw previously. So I finally had to tell you, we add AJ. And then people, oh, okay, because it should be pretty obvious. If we want, so, you know, you have all the vectors around the circle of radius A centered at the origin, that's fine. Just add AJ to it, and every one of these points moves over to this circle. Okay? And every R vector, and I could draw all the R vectors, you know, they come out here, and here, and here, and here, because all the X components translate. So you can see that we could put the circle anywhere now. I'm going to put the circle, and somebody, when I mentioned the pre-calculus, said, oh, that's the HK thing. And then he did it. Okay? Not as fresh as it might be, but if it comes back, that's sufficient. Okay. So anyhow, you want to put it at HK? You want to get that circle radius too? You just do and of course, this is Y and this is a Z. Okay. You just add HI. That's our HJ plus A K. Okay. So, okay, I probably shouldn't use HKs because that's the K. So let's say we want to translate it to Y naught Z naught. So then we add 1 lot I plus Z naught K. And of course, we then you'll probably write this as V cosine U plus Y naught. It's not I, it's K plus D sine U plus Z naught times K. Right. It's very easy to move circles. Yeah, it's not all that hard, but you're not going to get into that. Probably not going to get into it at all. Make sense? Okay. Good. Okay. That's a little bit about parameterization. You really want to look at all the examples. Parameterize as many things as you can. As we do folks, we really need the parameterization. We do surface samples. Now let's talk a little bit more about how some of this stuff works. Okay. You've seen the way the text does this with TU, which is partial derivative of R with respect to U. It's actually just RU, which is negative D sine U I plus V cosine U sine K. Okay, now I'm a little concerned about legibility, doggone it. You know, most of the stuff that I just said over here wasn't visible because I was a little careless. About the board. And now it's out of focus again. Oh, it came back in focus without seeing the R part. Okay, real quickly. People got this parameterization, same parameterization we saw before. Didn't say that you just shift this thing by adding AJ. So you're going to add the AJ vector to every R vector, which gets you a vector on circle out here, because the circle we're trying to do, well, I did introduce that. Okay. So, and then if we want to move out to put the circle anywhere, it's pretty obvious what we do. When I take it out to Y naught Z naught, we just have Y naught J, we have Z naught K. And then we can, of course, express this all as a multiple K and a multiple K. There's some advantages to this, though, because you see your basic circle, then plus your constant transformation. So this isn't a bad way to express it. Put parentheses around this, parentheses around this, to really see what's going on, because if you see it in this form, you don't necessarily factor it out to this form. Okay, not really factoring it out. You don't really range it to this form. So you want to understand both forms. Okay, so I know what we're saying here. Okay, if you take the U derivative of a vector function, we get this. What this does, this vector compares to this vector being perpendicular to. Okay. And then, well, let's just do CV. Okay. We can see that these two vectors are perpendicular in this case. It's not always true for any parameterization. Now, what's TU cross TV? Well, for this pair of simple vectors, I'm going to use just a distributive law. I cross I is 0, I cross J is K. Right? So you're going to get negative V sine squared U K. Okay. And then this cross with the IJ cross I is negative K. So you get negative V cosine squared U times K, which is just negative V times K. What's the area? It's magnitude of TU cross TU. TU dV, or delta U delta V. Okay. What's the area of this? It's your V, your sample point, times delta U times delta V. Okay? Cross product. So that indicates this, of the area of this maps to the area of this. This only has an area of delta U times delta V. This has area V delta U delta V. Now, of course, you can identify U with theta, your angle. You can identify V with R, your radial. Your radial component of your forward vector. Okay. And right there is a factor for an integral polar coordinates, right? Okay. So it all kind of comes full circle. Understanding this is a mapping where you're exaggerating the area of this. So if you want to think about it a little bit. It's not necessary that your U and V give you perpendicular vectors, because when you do the cross product, you get the area of a parallelogram. Parallelogram in this case happens to approximately be a rectangle. But it's not always the case. So you want to use cross product and use the magnitude, because that's of the area. So that's a factor by which the area up here increases. Okay, that's kind of important to understand. I want to then talk a little bit more about this shape. What's its surface area? So let's pose that question. Let's see how I want to pose it. Well, what's your 2u, what's your 2v, and what's the cross product? So this. My pretty blue. I haven't used it. Okay. Okay, now, a little confusing. I've got this along with this, so let's kind of wall this off and make sure we understand. Let's talk about all this stuff here. For R equal V cosine ui plus V sine uj, all this stuff. Okay. Now the question is, what's this give us? Well, this gives us this picture. Where's your 2u, where's your 2v, what's our cross product, and what's it make? Give it a shot. Okay, a little confusion here. Doing an R prime and an R double prime, that isn't it. Okay, it's the U derivative and the V derivative. There's geometric reasons for that. Read about it in the book. Because we don't have time today to develop it. And I've been using vectors all my U and my V. That's totally inappropriate. U and V are parameters, they're not vectors. But while I was doing that, I will. Okay, so RU is what? It's negative V sine UI plus V cosine U. Okay. Okay. Turns out that at any point you get for U and V, that gives you a point on the surface, and this vector is tangent to the surface at that point. Again, read about why. UV equals RV. We'll call this T because it's a tangent vector. And that's going to be two V rhymes with T. But there it is. Okay. This is tangent. So if you have given UV, you've got a point here, and you've got a vector here that's tangent, and it's in the Z equals constant plane or whatever plane that is these days. So it's like your TU is here. Okay. And then your TV is, okay, this vector lies above parallel vector down here in the plane, since it's parallel to the XY plane. So cosine U plus sine, cosine UI plus sine UJ is perpendicular to this. You take the dot product to see that. So you got a vector here. But when you go up here, the vector that you get that's tangent to the plane is no longer parallel to the XY plane. Okay, it's got a K component. So it's kind of parallel to this thing, but it's up a little bit. So it's maybe like this. Now, that can kind of make sense in terms of this surface. And you're out here, and you got a vector here and a vector here. And the cross product of these vectors is going to be normal to the surface. So So you've got your TU cross TV. Here's your TU, here's your TV. Your TU cross TV. Has a couple of really good properties. It tells you how a UV increment down here expands when you get up here. Just directly above this, there's a surface area increment, and it's at an angle. Being at an angle, its vertical shadow is still here, so it's got to be bigger. Okay, but the sun's directly above, and I move my hand like this, the shadow gets smaller, right? Okay. So if I want the shadow to cover a given area down there, I've got to grow a bigger hand. When I turn it so that the area that it projects to gets bigger. Okay. When to think about that, think about the area increment you get up here. So you've got a area increment down here. You've got a bigger area increment up here. And the factor by which the area increment grows due to the slope of the parabola. Okay. It's the magnitude of TU cross TV. So now we're mapping the same thing here. But instead of mapping just to a circle in the plane, we're mapping to this region above the circle in the plane. Because by adding this, we get points above the circle. In our new TU and TV, give us the magnitude of the cross product of those two, tells us how much the area is expanded here. So that's a basic idea. That's why you need to be able to parameterize these things. And once you parameterize them, the process is actually pretty simple. You just take some derivatives. Hopefully you don't just plug in this sense of plugging into a formula. I hope you plug into something you understand. And I'll talk about how to understand it. But the process itself is fairly straightforward once you get the parameterization. The parameterizations you have in your homework are actually fairly straightforward, not any more complicated than this one. Just a lot of circles and then some other stuff. Okay. So that's the whole process of doing surface integrals.